As we begin discussing probability, we're going to first start with the counting principle. I'm going to start with a couple of examples, and I want you to note the difference between these two. So we're going to take a standard deck of 52 cards. We're going to draw one card, replace it, and draw another. So the first time when I draw that card, I'm going to get one card out of 52. So there are 52 choices. Now after I look at that card and put it back, I'm going to draw another card. There are still 52 choices. That's all because I replaced my first card. But notice what happens if I do the exact same thing with the standard deck of 52, but when I take my other card, I don't replace the first one. So there are 52 choices now for my first card, but there's only 51 choices for that second card. So this is going to become important when we start talking about probabilities, specifically permutations and combinations. But what I demonstrated with both of these is the counting principle. Now the counting principle states if the first event has m ways of happening, and the second event has n ways of happening, then the total ways of event 1 and event 2 can occur is m times n. So I'm going to go back to my two examples. In order to do this first example, I take 52 times 52. If I multiply that out, that'll tell me the total number of ways I can draw two cards with replacement. If I take 52 times 51, that'll tell me the total number of ways I can draw two cards without replacement. So let's look at a couple more examples to kind of put this in perspective. So using the counting principle, if I go to a sandwich shop and they have 3 bread choices, 5 meat choices, and 4 sauces that I can put on top of my sandwich, if I want to find the total number of ways of making a sandwich, I'm going to take the 3 breads times the 5 meats times the 4 sauces. So I take that and multiply it out. There are 60 ways of making a sandwich with 1 bread, 1 meat, and 1 sauce. Another example, think about your initials. There are 26 letters in the alphabet, so there are 26 letters for my first choice. Because we can have repeats, because we're replacing the letters, there are still 26 choices for your second, and there are still 26 choices for that last initial. So if I take 26 times 26 times 26, I'll have the total number of ways that somebody can have their initials. Another example would be phone numbers. Now you cannot have a first digit of 0 or 1 in phone numbers. So if I take a phone number without the area code, there are only 8 choices for that first number. But there are 10 choices for all of the other ones because you can have repeat numbers. Now if I said I want a unique phone number that has no repeats, that would totally change this. Same thing with license plates. In Iowa, our license plates typically have 3 letters, but they can have repeats. And 3 numbers, but they can also have repeats. Now, if they would change the laws or change the rules on our license plates and say you can't have any repeats, then these numbers would definitely change because I'm not replacing the letter after I use it. Same thing with the numbers. And I'd have a different number of ways of this happening, but all of these fall under this big umbrella of the counting principle. So to continue our discussion about counting principle, there are 2 different calculations that we're going to do. The first one is called a combination, the second one is called a permutation, and there is one small thing that makes them different. Notice in a combination, there is no order of the items that we choose. So I will give you an example, and I like to use the word choose because of the capital C. If I have 10 items and I'm going to choose 3 of them to use for something, and it doesn't matter any order, I'm just choosing 3 of them, it'd be considered a combination. Now, the calculation for combination uses this notation Sometimes it uses this notation, but they mean the exact same thing. But notice we've got a factorial of the number of items. We subtract the number of items and how many we choose, do that factorial, and do another factorial of the number of chosen items. Most calculators, a lot of the online graphers that we use, has this calculation built in, but this is how you do it otherwise. So an example, if I have 20 students in a class and we're going to choose 4 of them to be on a committee, there is no order to them. There is no first, second, third. There's no president, vice president, secretary. There's no order. There's no advantage to being first versus being fourth. So this is definitely a combination. I am doing 20, choose 4. Now, I can certainly work through this. I can plug this into my calculator to figure out what this is. I have a 20 factorial, I have a 16 factorial, and I have another 4 factorial, and I can calculate that out. Another example of a combination. If I'm going to get a hand of 5 cards from a standard deck of 52, doesn't matter when I get which card, I have all 5. There's no advantage to getting one card first versus that same card last, so this is definitely a combination. I am choosing. I have 52 cards, and I'm choosing 5 to be in my hand. And sometimes we will write it this way. That's all the different ways that I can choose 5 cards out of a deck of 52. Now, the one that complements this is a permutation. Notice now that the order does matter for those items that we pick. And I like to use pick to distinguish from combination because pick has a P in it for permutation. So the number of items, and we're picking a certain amount. Now, the calculation looks very similar except that extra R factorial isn't here. So this is actually a little more exclusive because order matters. Order matters for the permutation. So if I have 10 items and I'm going to pick 4 of them and put them in order, I'm dealing with a permutation. Now, there are a couple of things we have to keep straight here. If we select all the items, let's say I'm going to take all the students in a class and I'm going to line them up from first to last. If I'm selecting all of them, this goes away and it's just the n factorial. So if I have 15 students in a class and I'm going to list them 1 through 15, there's 15 factorial ways of doing that. It's a lot of ways. The other thing we have to talk about is if there are repeats. So if there are repeats, then we have to deal with what we call distinguishable permutations. So this is a little different, and I'm going to talk about an example with this. But with distinguishable permutations, we start with that same n factorial, but we have to divide out the repeats. So let's get into a couple of examples. First, just a permutation. Think of a cross-country meet that has 50 participants, and we're going to pick first, second, and third place. So now we have 50, and we're picking 3. So the calculation would look like 50 factorial over 47 factorial, because I subtract those two things, and I reduce that a little bit. Notice that this 50p3, or this NPR, and this NCR are both built into most calculators, graphing calculators, online graphers, things of the like. So you can do this calculation, or you can have your calculator do that calculation for you, but this is what it's actually doing. Now, these are a little easier to do by hand because 47 of them are going to cancel. And whatever 50 times 49 times 48 is all the ways that I can pick first, second, and third. Taking letters and rearranging letters. I have 3 letters here. I'm going to rearrange these 3 letters. I'm using all 3 letters. Now, the interesting thing is 3 factorial is 3 times 2 times 1. There's only 6 ways of doing this. And again, order matters. So I have CAT, CTA, ATC, ACT, TAC, and TCA. Those are my 6 ways. I used all of them, so I used this version instead of this. But you could still plug in 3, pick 3, and it'll get you all 6. So that calculation still works. But let's talk about this idea of distinguishable permutations. Interesting. So I used my name, and I wrote it up here twice. And I'm wondering if you can tell the difference between those two. Most people say, no, I can't tell the difference. But I actually took the ends and switched them. But it's not distinguishable because the word that it makes looks the same. So when we start talking about permutations and we want distinguishable permutations, we have to take into account the repeats. I actually have 2 different repeats in my last name. So I have 6 letters, so I'm going to rearrange all 6 letters, but I have 2 A's, so I have to take out that repeat, and I have 2 N's, I need to take out those 2 repeats. So this is going to give me all the unique permutations, things that are distinguishable, and it's going to take out the H-A-M-A-N-N and the H-A-M-A-N-N, which look alike. Let's add a little complexity to this. If you throw in my first name, we now have 11 letters to rearrange. But I have 4 A's that are repeats. I have to divide those out. And I also have 3 N's that I have to divide out so that I get unique permutations, things that are distinguishable from just any other permutation. The important part with these, permutation, we have an order to them. Combinations, we don't have an order, and that's what we look for to decide which one of these we're going to use.